You're settling into the cockpit for a 7-hour flight from New York to London. Looking at the flight plan, you naturally expect to point the nose of the aircraft toward the destination and fly in a straight, direct line. But if you watch the instruments, you will notice a paradox. Your flight management computer is navigating the shortest physical path possible, yet your magnetic and true headings are constantly changing throughout the flight. Looking at this split-screen comparison, you can see why. Maps are flat, but the Earth is a sphere. A straight line drawn on a flat piece of paper translates to a curved, tight string across the surface of a 3D globe. As that tight string crosses the Earth, it intersects each vertical longitude line at a slightly different angle. This diagram illustrates two navigation tracks. A great circle represents the shortest physical distance, requiring a constantly changing heading. A rhumb line provides a constant, easily flyable heading, but results in a longer physical path. Because of the Earth's spherical geometry, navigators mathematically translate a flat, constant heading into a curved physical reality to fly efficiently across long distances. Notice how the vertical meridian lines on this globe are wide apart at the equator, but angle sharply inward to meet at a single point at the North Pole. We call this physical leaning Earth convergency. To calculate exactly how much these lines lean toward each other, we multiply the change in longitude by the sine of the mean latitude between our 2 points. Since a rhumb line gives us our constant average heading, and the great circle is our actual curved flight path, we need a mathematical tool to bridge the gap between them. That tool is the conversion angle. As this geometric arc shows, the conversion angle is always exactly 1/2 of your calculated Earth convergency. Finding these two exact numbers is the mandatory first step before you attempt to solve any track-finding question on a DGCA exam. A common friction point for students is trying to rote memorize when to add or subtract that conversion angle. This usually leads to confusion under pressure. Instead of memorizing, look at this diagram and visualize the golden rule of navigation. The great circle is always closer to the pole than the rhumb line, of no matter which hemisphere you are in. Let's put that into practice. We need to calculate a flight from point A at 60 degrees north, 050 west, to point B at 60 degrees north, 010 west. Because we are traveling straight along a parallel of latitude, our rhumb line track is 090 degrees east. Running the coordinates through our formulas gives a change of longitude of 40 degrees and a mean latitude of 60. That makes our convergency 34.6 degrees, and our conversion angle 17.3. Applying the golden rule to our grid, we know we are in the northern hemisphere, so the great circle must bound north toward the pole. To point our aircraft further north than 090 degrees, we subtract our conversion angle. Our initial track is 072.7 degrees. As the curve arrives at the destination, it points further south to rejoin the rhumb line. So we add the conversion angle to 090, giving us a final track of 107.3 degrees. Taking 5 seconds to sketch that curve relative to the pole replaces the need for memorization with spatial logic. This provides a visual check for your calculations before you commit to an answer. Now let's look at the specific edge case scenarios DGCA examiners use to trick you into performing unnecessary, time-wasting math. First is the equator trap. As you can see here, the longitude lines along the equator are parallel. The sine of 0 degrees is 0, meaning convergency along the equator is 0. Then there is the meridian trap. If your flight path travels strictly north or south along a single longitude line, your change of longitude is 0. In both of these traps, the rhumb line and great circle tracks are identical. You also have to pay attention to how map choice distorts these lines. On a Mercator projection like this one, rhumb lines are drawn straight, but on a Lambert conformal projection, it's the great circles that plot as straight lines. Keep this cheat sheet in mind when you walk into the exam hall. Know the definitions, write down the two formulas, always sketch the bend to pole rule, and spot those zero convergency traps instantly. Mastering this spatial geometry helps secure high marks on your exams and builds the foundational spatial awareness needed to navigate modern aircraft across the globe.